objectives of this particular lecture are to describe salient features of some of the important types of evaporators, discuss thermal design aspects of refrigerant evaporators, present correlations for estimating heat transfer coefficients, and discuss Wilson's plots. So at the end of the lecture you should be able to describe important features of some of the important types of evaporators, explain the complexities to be considered in the design of refrigerant evaporators, estimate heat transfer coefficients using the correlations presented, and finally use the concept of Wilson's plot and estimate various heat transfer coefficients. So let us look at a very important type of evaporator called a shell and tube type evaporator. As the name implies, this kind of an evaporator consists of a shell and a large number of straight tubes arranged parallel to each other. In dry expansion type, the refrigerant flows through the tubes, while in flooded type, refrigerant flows through the shell. So let me show the picture of a dry expansion type shell and tube type evaporator. So this particular picture shows the shell and tube type evaporator where the refrigerant flows through the tubes. You can see that the refrigerant flows through the tubes while the water flows through the shell. Okay, so this is a two pass, you can call this as a two pass as far as the refrigerant is concerned, because the refrigerant flows through the tubes like this, then takes a U-turn, and again it flows in this direction and finally leaves the evaporator here. Okay, in any shell and tube type of evaporators, baffles are provided in the shell side. You can see that these are the baffles. Okay. The purpose of the baffles is to avoid stagnant zones and also to improve turbulence so that you can get good heat transfer coefficient on the shell side. For example, you can see that because of the presence of the baffle, water is forced to flow like this. Okay, so short circuiting of water is prevented, thereby you can get good heat transfer coefficient and the stagnant regions can be avoided. Of course, the baffles increase pressure drop through the shell side, so the baffles have got to be optimized. So this is the direct expansion type shell and tube type evaporator. As I said, since the refrigerant flows through the tubes, at the end of the tubes you can have superheating. Okay, that means what refrigerant goes out can be a superheated vapor. Okay, now let us look at the other features. The shell diameters normally range from 150 mm to 1.5 meters. The number of tubes may be less than 50 to several thousands, and the length of the heat exchanger may be between 1.5 meter to 6 meters. Normally steel tubes are used with ammonia, while copper tubes are used with freons, and when we use freons, the heat transfer coefficient obtained on the refrigerant side is typically small. So we normally use what is known as integrally finned tubes on the refrigerant side, whereas in case of ammonia, since the heat transfer coefficient is large, fins are not required. Dry expansion type evaporators uses fins inside the tube, that means on the refrigerant side, while flooded type uses fins outside the tubes, because in the flooded type refrigerant flows on the outside of the tubes. Dry expansion type requires less refrigerant and has positive lubricating oil return. That means the lubricating oil return to the compressor is ensured in dry expansion type, and the amount of refrigerant charge required inside the system is also less. And these dry expansion type shell and tube type evaporators are normally used for small and medium capacity refrigeration plants. That means the capacity ranges from about 2 tons to 350 tons. Whereas the flooded type evaporators are available in larger capacities ranging from 10 tons to thousands of tons. Okay, in very large plants, flooded type evaporators are used. So now let us look at flooded type shell and tube evaporator. As I have already mentioned, the liquid, that means the external fluid, which is usually either brine or water, which is to be chilled, flows through the tubes, and the refrigerant is fed through a float valve which maintains a constant level of liquid refrigerant in the shell. Both single and multi-pass arrangements are possible, and these are also available in vertical configuration. Since the shell is not completely filled with liquid refrigerant, superheating is also possible. So this picture shows the flooded type shell and tube evaporator. As I have already told, in this case refrigerant is on the shell side, okay, whereas the water flows through the tube side. Again, this is a two-pass arrangement as far as water is concerned, because water flows through the tubes like this, takes a U-turn and again flows back in this direction. Okay, so that means the water crosses the refrigerant path twice. So you call this as two-pass arrangement. Okay, you can see that this is the liquid refrigerant level. Okay, liquid refrigerant level. So this is maintained by a float valve, and the entire shell is not filled with liquid. Okay, you can see that there is an empty space in which refrigerant vapor is there, but not the liquid. Okay, this is required to prevent the exit of refrigerant liquid droplets along with the vapor. Okay, and since you have some space above the liquid level, superheating is also possible in this kind of arrangement. Okay. Now let us look at shell and coil type evaporator. These are of smaller capacity than the shell and tube type. These are made of one or more spiral shaped bare tube coils enclosed in a welded shell. So this is almost similar to shell and coil type condenser, which was discussed in an earlier lecture. In shell and coil type evaporator, refrigerant can flow through the coil in direct expansion type or through the shell in flooded type. In direct expansion type, the large amount of water in shell provides what is known as a hold up capacity. That means a large thermal storage capacity is provided by the amount of water in the shell, and this is known as hold up capacity. And this type is good for small but highly infrequent peak loads. Now let us look at double pipe type evaporator. As the name implies, this is almost similar to in construction to the double pipe type condenser. Again, this consists of two concentric tubes. The refrigerant flows through the annular passage, while the liquid being chilled flows through the inner tube in parallel flow or counter flow. These may be used in flooded as well as direct expansion mode. This type of evaporator requires more space than other designs. Shorter tubes and counter flow gives good heat transfer coefficient. And the outer tubes need insulation to minimize heat leaks. Insulation is required because the refrigerant flows through the annular space. Okay, and refrigerant temperature is much lower than the ambient temperature. So to reduce heat leaks, you have to insulate the outer tubes. As far as the space occupied is concerned, the shell and tube type evaporators occupy much less space compared to other types of evaporators. And the volume is also quite small. Okay, that is the reason why the shell and tube type of evaporators are very commonly used in large capacity systems. Okay, whereas the tube in tube types of systems which occupy more space are generally used in smaller capacity systems. Okay, now let us look at the next type. This is what is known as Bordello type evaporators. This kind of an evaporator consists of a large number of horizontal pipes stacked one on top of other and connected together by headers to make single or multiple circuits. The refrigerant is circulated inside the tubes either in flooded or dry mode. That means you can have flooded evaporator or dry expansion type evaporator. The liquid to be chilled flows in a thin layer over the outer surface of the tubes. The liquid flows down by gravity from distributed pipe located on top of the horizontal tubes. Now let me show the picture of Bordello type of evaporator. So this is the header. Okay, so this is one header on this side, and this is another header on the refrigerant inlet and inlet side. Okay, this is the header on the outlet side. So to this header, a large number of refrigerant tubes are connected. These are the refrigerant tubes. Okay, refrigerant tubes through which the refrigerant flows. So the refrigerant enters into the header, and from the header it enters into the several parallel tubes. Okay, and it extracts heat from the cool liquid being chilled, and it exits from this header. Okay, so from this header it goes to the compressor. Now the liquid being chilled, for example milk, it enters into the header which is kept at the top. Okay, you can call this as header or distributor. This has several nozzles. Okay, you can see that these are all the nozzles. Okay, through these nozzles the liquid that is being chilled falls onto these refrigerant tubes, okay, because of gravity. So gravity is in this direction, so the liquid falls on the tubes and it trickles down, right, and finally it gets collected in the bottom tank, right. The chilled milk or chilled water gets collected in this bottom tank, okay. From the bottom tank it is taken out, right. So if you look at a single tube, you will find that you have a single tube like this, okay. This is the wall of the tube. Through this tube refrigerant is flowing, and outside a thin layer of liquid gets collected, okay. So outside you have liquid layer, okay. This liquid is the liquid that is being chilled. So since this has a small thickness, the heat transfer will be quite effective here, okay. So this is known as Bordello type evaporator. So you can see that the liquid to be chilled is open to atmosphere. That means it is at atmospheric pressure, hence its aeration may take place during cooling. Bordello evaporator is widely used for cooling milk or cooling wine and for chilling water for carbonation in bottling plants. One advantage of this kind of an evaporator is that the liquid can be chilled very close to its freezing temperature, since freezing outside the tubes will not damage the tubes, okay. So this is one of the advantages of Bordello type of evaporator. Next, let us look at the direct expansion plate fin and tube type evaporator. This, as the name implies, the plate fin and tube type evaporator is constructionally similar to plate fin and tube type condenser, okay. So here the external fluid is air, right. In case of condenser, also the external fluid is air and the refrigerant flows through the tubes. So in case of plate fin and tube type of evaporator, also the refrigerant flows through the tubes while the air flows outside the tubes, okay. These evaporators are used for cooling and humidifying the air directly by the refrigerant flowing in the tubes. The liquid refrigerant enters from top through a thermostatic expansion valve. This arrangement makes the oil return to compressor better rather than feeding refrigerant from the bottom of the coil. The fin spacing varies from 50 to 500 fins per meter length. So let me show the picture of this. So you can see that constructionally this is almost similar to your plate fin and tube type condenser, okay. So the refrigerant which flows through this tube enters at the top, right. It flows like this through the tube, okay, and it leaves the evaporator at the bottom. Of course, you can have several rows of such tube. That means you can have one row behind the other, and outside you have the fins, and these fins, remember, they are plate fins, okay. That means if you look from the side, you have the fin and these are the tubes, okay. So this is the side view, if you see from this side. And here the air which flows over the tubes and fins, it gets cooled as it comes in contact with the evaporator surface, and depending upon the surface temperature it may also get dehumidified, okay. That means both the temperature as well as the moisture content of air may reduce as the air flows through this kind of an evaporator, okay. And as I said, normally the fin spacing varies from 50 to 500 fins per meter length. In evaporators, the atmospheric water vapor condenses on the fins and tubes when the metal temperature is lower than dew point temperature. Actually, this is one reason why the design of evaporators, that is especially where air is the external fluid, is quite complicated compared to condensers. Because when the refrigerant temperature is low and when the surface of the evaporator is at a temperature lower than the corresponding dew point temperature of air, then the moisture in the air will condense. That means on the evaporator surface you have both heat as well as mass transfers, okay. So in the design of the evaporators you have to consider both heat transfer rate as well as mass transfer rate. The mass transfer rate will give rise to latent heat transfer rate. That means both sensible as well as latent heat transfer rates have got to be considered while designing the evaporators for cooling and dehumidifying applications. And as we have discussed in our earlier lectures, cooling and dehumidification is mainly required in air conditioning plants. Of course, in some of the cold storages also cooling and dehumidification is required, okay. So this is one of the common requirements. And as I said, the difference between a plate fin and tube type evaporator, and condenser is that in the condenser air does not undergo any latent heat transfer, whereas in the evaporator both sensible as well as latent heat transfer takes place on the air side also. Okay. And if the surface temperature is less than 0 degree centigrade, then frost also may form. That means whatever liquid condenses, it will also freeze if the surface temperature is lower than 0 degree centigrade. This happens in domestic refrigerators and all. You must have seen the evaporator of domestic refrigerator being covered with a thick layer of frost, because the evaporator operates at a temperature much lower than 0 degree centigrade in a domestic refrigerator. Hence, for low temperature coils, so what is the consequence of this? We have to consider this one while designing. So what is done is, for low temperature coils, that means the coils which operate at low temperatures such that frosting may take place, a wide fin spacing, that means about 80 to 200 fins per meter, is used to avoid blockage of flow passage due to frost formation. That means you cannot afford to have very close fins when there is a possibility of frosting taking place on the air side. Okay, if the fin spacing is very close, then if frost forms, then the frost will very soon block the air passages. Okay, once the air passages are blocked, air cannot flow. Okay, so that is the reason why in evaporators used for domestic refrigerators or in cold storages where frosting takes place, the fin spacing has got to be wider. So as I have mentioned in an earlier slide, the fin spacing is normally between 50 to 500 fins per meter, as long as there is no frost formation. Okay, if the frost formation is there, then the fin spacing varies from about 80 to 200 fins per meter. And in the commercial evaporators, you will find that the fin spacing may not be uniform. Okay, especially if the fin is not plate fin tube type. Okay, typically in domestic refrigerators and all, the fins are provided in such a way that at the inlet where the frost formation is much faster, the fin spacing is higher. Okay, and as the air gradually moves up, the fin spacing is gradually reduced so that you can have higher heat transfer. Okay, so this is a very important aspect to be considered in the design of evaporators which are likely to get frosted. Okay. And since you cannot allow the frosting to take place continuously, frequent defrosting is required. In air conditioning applications, a typical fin spacing of 1.8 mm is used. That means in air conditioning applications, the fin spacing can be slightly higher compared to the evaporator used in domestic refrigerators, because in air conditioning applications, water condenses, but it does not form frost. If it forms frost, then frost cannot leave the evaporator surface. Okay, it sticks to the evaporator surface, then it starts blocking the airflow passage. Whereas if water only condenses, then due to gravity it can trickle down. Okay, it will not affect the airflow passage. That's the reason why in air conditioning applications the fin spacing is much smaller compared to a domestic frost-free evaporator. Okay. Now let us look at plate surface evaporators. One type of plate surface evaporator is also known as roll-borne type evaporator, and this is normally used in conventional domestic refrigerators. Okay, that means not automatic refrigerators, but refrigerators in which frosting has to be done manually. Okay, so let me show the picture of a roll-borne type evaporator. This is a roll-borne type evaporator. Okay. So it basically consists of a plate which consists of refrigerant tubing. Okay, so this is refrigerant passages. I should not call it a tubing, but this is refrigerant passage. Okay, through which the refrigerant flows. For example, refrigerant enters like this, flows this way. Okay, and finally leaves like this, and air flows over the outside. That means on this surface you have air, and if you take a section at, let us say, at A, the section looks like this. Okay, so this is your plate. Okay, and this is your refrigerant. Okay, and air is on the outside. So the manufacturing of this is quite interesting. What is generally done is two aluminum plates of equal size, that means equal thickness, equal width, etc. are taken, and on these aluminum plates the refrigerant circuit is printed. That means it's just like your PCB, okay, printed circuit board. The refrigerant tubing circuit is printed on this. Printing means some ink is deposited in the way the tubing is required. Okay, so once the printing is done, both these aluminum plates are brought together and both the plates are sent to rolling mills. Okay, so both the plates are rolled in rolling mills. So when the plates are rolled in let us say hot rolling mills, then bonding of the two plates takes place. That means both the plates get fused together and they form a single plate. This bonding takes place everywhere except where there is ink. Okay, so wherever there is ink, the bonding does not take place. Okay, that is the characteristic of the ink used. Okay, so after the rolling process, what is done is the refrigerant passage, that means wherever ink is there, is inflated by sending high pressure water or high pressure air. Okay, since there is no bonding wherever there is ink, at that point under high pressure the tubes, the plate can get inflated. Okay, that means plates remain separate only where there is ink. Rest of the place they get fused. Okay, since they are separate where ink is there, they can be inflated by sending high pressure fluid. Okay, so once the high pressure fluid is sent, the refrigerant flow passage is formed. Okay, so once the passage is formed, the high pressure is withdrawn, then it is cleaned, right. So what you have is a single plate, okay, which is made of two separate plates, a single plate consisting of inbuilt refrigerant passages through which refrigerant can flow. Okay, so that is what is shown here. You have the finally, when everything is over at this point, the inlet and outlet tubes are welded to the roll bond type evaporator. Okay, so through this tube refrigerant enters and from this it comes out, and this plate can be bent into any form. For example, this plate can be made into the form of a box, or it can be made into the form of a U, it can be bent into the form of L, right. So it can be bent into any shape, and this is nothing but your evaporator, and it also is nothing but your freezer box. This is what you see in a conventional domestic refrigerator. The moment you open the door, you find a freezer box. Okay, and you will also notice that the freezer box consists of some protrusions. Okay, and freezer box is made of aluminum plate, and it has some protrusion. That is nothing but your refrigerant flow passage through which the refrigerant flows. Okay, this kind of evaporator is very effective, and it's also easier to manufacture, and it is cost wise also it is good. It is cheaper compared to the tube and plate type evaporator. Okay, that's the reason why most of the manufacturers nowadays use this kind of evaporators in domestic refrigerators. Okay. And in addition to that, because of very good bonding, the heat transfer is very effective. Okay, and if you look at any single tube, you find that this area acts as a fin. Okay, and the contact resistance between the fin and the refrigerant is almost negligible. Okay, because they are formed of the same plate, right. So these are the advantages of roll bond type of evaporators, which are used in conventional domestic refrigerators and other applications. There is another type of plate surface evaporator. In this type, a serpentine tube is placed between two metal plates such that the plates press onto the tube. Okay, so let me just describe it first. The edges of the plates are welded together. The space between the plates is either filled with a eutectic solution or evacuated. If eutectic solution is provided, it provides a good hold up capacity. And these kind of evaporators are widely used in refrigerated trucks. Okay, so let me describe this. So you can see here, okay, and this is the cross sectional view at A, right. So if this is like a closed box, right, a closed box in which the refrigerant tubes, okay, the serpentine tube is sandwiched, right. That means you take two plates and put this serpentine coil and close all the wedges, right, and have the inlet and outlet, right. Now you have some space between the refrigerant. This is the refrigerant tube. Okay, these are the refrigerant tubes, and this is the plate over which your air flows, air or whatever is the external fluid that flows, right. So there is a gap between the tube and the plate. Okay, so all this space. So that space is normally filled with a eutectic solution. Okay, eutectic solution means a solution which has low freezing point, right? So when you fill this space with the eutectic solution, that means this space, then there is a good thermal contact between the refrigerant tube and the outer plate. Okay, because the eutectic solution, which is a liquid, has a high thermal conductivity compared to air or vacuum. So as a result, you get good performance. Okay, in another method, what is done is this space is not filled with any solution, but it is evacuated. Okay, when you evacuate it, the outside pressure, which is atmospheric, that presses these two outer tubes. As a result, again good thermal contact is formed between the tubes and the plates, right? But more widely the eutectic solution is used, because the advantage of eutectic solution is that in addition to providing good thermal contact, it also provides what is known as hold up capacity. That means when you have a lot of solution in the evaporator, okay, a lot of external fluid in the evaporator, the external fluid has, since it is a liquid, it has large specific heat, right, and it also has large mass because of its high density. Okay, so you have large MCP liquid which is cooled to almost the same temperature or few degrees higher than the evaporator temperature. Okay, so that means the entire, you have a pack or you have an evaporator which has high large thermal capacity and which is cooled to a low temperature. Okay, now let us say that there is a power cut. Okay, if there is a power cut, then refrigeration is not provided, refrigerant system doesn't work, so no refrigeration is provided because the compressor doesn't work. But still, because of the large hold up capacity, that means because of the large amount of liquid which is originally present in the evaporator and which was at very low temperature, the refrigerated space can be maintained colder for a longer time. Okay, that means this liquid, the eutectic solution, continuously gives cooling as long as its temperature is low. Okay, so this kind of capacity is known as hold up capacity. Okay, so this is one of the advantages of having this eutectic solution. Okay, it can take care of power cuts or load variations, etc. Okay, and this is very widely used in refrigerated trucks. What is done in a refrigerated truck is these evaporators are connected to refrigeration systems which are on the land. Okay, so just before the truck starts, all these evaporators are cooled to the required temperature. That means the eutectic solution is cooled to the required low temperature. Okay, then the evaporators are disconnected from the refrigeration system and they are placed in the refrigerated truck. Okay, then the truck moves from one place to the other. So as long as the truck is on the move, cooling is provided by the cold solution placed in the evaporators. Okay, so that way it is a simple system, and evaporation is, or I am sorry, cooling is ensured even when the truck is moving without putting any refrigerant system on board. Okay, so this is one of the popular ways of providing refrigeration. Okay. Now let us look at another very important type of evaporator, what is known as plate type evaporator. Plate type evaporators are used when a close temperature approach, that means 0.5 Kelvin or less, between the boiling refrigerant and the fluid being chilled is required. Okay, that means let us say that refrigerant is at minus 20 degrees centigrade and I want to chill the external fluid to minus 19.5 degrees. Okay, that means refrigerant temperature and the external fluid temperature are almost same. Okay, the difference is very small, about 0.5 Kelvin. Then you require very high heat transfer coefficients and all. Okay, and you also require basically very high heat transfer area also, right? In such cases the plate type evaporators are used. Okay, that means wherever you want very close approach, plate type evaporators are used. These evaporators are widely used in dairy plants for chilling milk, in breweries for chilling beer, etc. These evaporators consist of a series of plates normally made of stainless steel, between which alternately the milk or beer to be cooled and refrigerant flow in counterflow direction. So let me show the picture of a plate type evaporator. So you can see here that there are a large number of tubes. For example, this large number of plates. Sorry, you have this is one plate and this is another plate. Okay, so like that a large number of plates are stacked together. Okay, and the flow passage is there between these two plates. Okay, that means there is some gap between these two plates through which the fluid can flow, right? For example, let us say that here the refrigerant is flowing in this direction. Okay, so in the passage formed by this plate and the next plate, that means in this passage the liquid being cooled will be flowing in the opposite direction. That means one fluid flows in this direction, the other fluid flows in this direction. Okay, so in the next passage, that means the passage formed between this plate and the next plate, again the refrigerant flowing will be flowing in this direction. Okay, that means if you look at the plates, let us say that these are the number of plates which are stacked together. If the refrigerant will be flowing like this, okay, in alternate paths, and liquid being cooled will be flowing like this. Okay, so this is refrigerant and this is the external fluid. So you can see that between the passages a true counterflow can be obtained. So as we know, the counterflow gives rise to very effective heat transfer. Okay, and you can also see that these plates are not plain plates, but they have some profile on that. Normally they have some structure in such a way that a good turbulence and hence high heat transfer coefficients can be obtained. Okay, normally herringbone structure or something like that is used. Okay, so the plain plates are taken and they are stamped with the required structure so that you get high heat transfer coefficient. Okay, so you have if you look at each plate, you will have this kind of stampings, and you can see that the refrigerant enters, for example, in this figure through the end plate. Okay, it enters like this, so flows through alternate passages. Okay, and it comes out like this. Okay, whereas water enters through this passage, again flows through the evaporator, and it comes out from this passage in the end plate. Okay, and the ends are closed. You have one end plate, this is one end plate and this is end plate, and when everything is put together, you also require a gasket to prevent leakage. For example, this is a gasket. So each plate will have gasket on both sides, and the gaskets will prevent leakage of refrigerant and also provide the gap for flow passage. Okay, so when you stack the plates together and close it with the end plates, then a closed evaporator is formed, and the entire evaporator is assembled. Okay, so you have the assembly tie rods and all that. Okay, so finally when you assemble it, you get a very compact evaporator which has very high heat transfer area. Okay, so high capacity, right? So this is what is known as your plate type of evaporator. Nowadays it is becoming popular, especially in large systems and also in the dairy plants and all where milk is used. The reason why it is becoming popular in dairy plants and all is that in dairy plants you have to clean the evaporators almost every day. Okay, because once the milk flows through it for a certain amount of time, cleaning is required, so to maintain the hygiene, right? And if you are using, let us say, a evaporator like shell and tube type of evaporator, cleaning is very difficult or it may take a lot of time. Okay, whereas in plate type evaporator, since the way it is constructed and by the way it is assembled, if you want to clean it, you have to remove some bolts, remove the end plate, then all the plates are accessible. Okay, so you can remove one by one plate and clean it and again stack them together and assemble the whole evaporator. Okay, so the removing the plates and cleaning and again assembling them back doesn't take much time. Okay, so this is very convenient in this kind of plants where hygiene is important, cleaning is required, frequent cleaning is required. Okay, so that's why these are very ideal. In addition to that, if you want to increase the capacity of the evaporator or reduce the capacity of the evaporator, all that you have to do is you have to remove the bolts, take out one end plate and add few plates if you want to increase the capacity, or remove some plates if you want to reduce the capacity. Okay, so capacity reduction or increase is possible very easily, right? That is the reason why these evaporators are becoming popular, in addition to their being very effective. Okay. And the overall heat transfer coefficient in plate type evaporator is very large. You get about 4500 watt per meter square Kelvin for ammonia water and 3000 watt per meter square Kelvin for R22 water. And these type of evaporators require very less refrigerant inventory for the same capacity. Okay, that means the total amount of refrigerant to be charged into the system is much less when you are using plate type evaporator. For example, it will be about 10% of shell and tube type evaporators for same capacity. Okay, so this is an advantage because it reduces the cost, and if you are using some toxic refrigerant, it is also safer to have less refrigerant. And cleaning the evaporator in dairy plants and breweries is very easy, as I have already explained. The capacity can be increased or decreased very easily by adding or removing plates. This also I have explained. Okay. So these are some of the important types of evaporators. In fact, if you look at evaporator, unlike condensers, there can be a large variety of evaporators. Okay, normally condensers can be made off the shelf, or you have standard types of condensers which can be made to order or which can be obtained off the shelf. But evaporators generally are made to order. Okay, most of the time the evaporators are non-standard depending upon the applications, except for maybe shell and tube type, or a plate fin and tube type, or a plate type. Okay, the roll bound type of evaporators etc. are made depending upon the requirement. Okay, the design and manufacturing etc. is done based on the specific requirement. So you have a wide variety of evaporators, okay, depending upon a wide variety of applications. Okay, this is one again the difference between evaporator and condenser. Okay, now let us look at the thermal design of evaporators. When I say thermal design of evaporators, actually the design of evaporator is very complicated, unlike the design of condenser, because of the factor that we have both, we can have both the sensible as well as latent heat transfer taking place on the external fluid side also. Okay, in addition to that, the prediction of refrigerant coefficient on the boiling side is also quite difficult, unlike that of condensation. Okay, for this reason the very exact design of evaporators is quite difficult. Okay, so there are a large number of correlations available which are applicable to particular ranges or particular flow patterns etc. So depending upon the type of the evaporator that we are planning to use, we have to use the suitable correlations. Okay, so I will not really go into the details of the exact design of evaporators, which you will normally study in an advanced course. I will simply explain the basic principles and the complexities to be considered while designing the evaporator. Okay, first let us look at the complexities. The design is complex due to refrigerant side heat transfer coefficient varies widely along the length. Both sensible and latent heat transfer may take place on external fluid side, as I have already told. Presence of lubricating oil in evaporator. Okay, in condenser normally if refrigerant is miscible with oil, then the presence of oil does not affect the heat transfer or pressure drop. But what happens is when you come to the evaporator, the oil tends to get separated from the evaporating refrigerant. Okay, that means once the liquid starts boiling, then lubricating oil gets separated from the refrigerant. Once it gets separated, it tries to stick to the evaporator tube and it tries to settle down in the evaporator. Okay, so this will complicate the design because you have to make sure that the refrigerant oil, lubricating oil is flowing back to the compressor, okay, to ensure that the compressor is operating properly. Okay, so oil return has to be considered while designing the evaporators. In addition to that, the presence of large amount of oil in the evaporator will also affect the heat transfer and pressure drop characteristics of the evaporators, which need to be considered. Okay, so this makes the design complicated. And evaporator pressure drop is more critical. That means this I have already explained in an earlier lecture. Compared to the pressure drop on the condenser side, the pressure drop on the evaporator side has a more significant effect on the performance of the system. Okay, so you have to design the evaporator in such a way that the pressure drop is less than the acceptable level. Okay, that means it is as far as possible, it should be as small as possible. Okay, this again puts constraints on the design of the evaporator. As I have already explained, refrigerant velocity has to be optimized, taking both oil return and pressure drop into account. And finally, the part load operation may lead to flooding of the evaporator, which may lead to slugging of the compressor. Estimation of heat transfer area and overall heat transfer coefficients. For plate fin and tube type evaporators, expressions for various areas are exactly same as that of plate fin and tube type condensers. This we have discussed in detail while discussing the design of condensers. So the how to calculate areas, that is exactly same. Okay. Expressions for overall heat transfer coefficient is also similar as long as there is no latent heat transfer on air side. Okay, if there is no latent heat transfer on air side and if only sensible heat transfer takes place on the air side, then the design, that means the expressions for U, expressions for various area, expressions for fin efficiency, etc., they are exactly similar for a plate fin and tube type of evaporator as that of plate fin and type tube of condenser, which we have already discussed, right. Expressions for U, LMTD and fin efficiency need to be modified if condensation or freezing takes place. Okay. On the other hand, if you have latent heat transfer on the external fluid side also, then you have to consider these aspects also. Now let us look at estimation of heat transfer coefficients. Air side heat transfer coefficients in plate fin and tube type evaporators. As I said, these evaporators are normally used in large in small air conditioning systems or in cold storages. If air undergoes only sensible heat transfer, correlations are same as that of air cooled condenser. Okay, that means air side there is only sensible heat transfer, then you can use the same correlation that we have used for condensers, namely for example Nusselt's correlation, Grimson's correlations, etc. Mass transfer effects have to be considered if water vapor in air condenses or freezes. Hence, analysis of cooling and dehumidification or cooling and freezing coils is more complicated due to simultaneous heat and mass transfer. Okay. So, to design cooling and dehumidification or cooling and freezing coils, one has to know the mass transfer aspects also, because you have to consider the simultaneous heat and mass transfer on the air side. Okay. This is quite complex and normally this is studied in advanced refrigeration courses. Okay. Now let us look at liquid side heat transfer coefficients. Liquid flowing in tubes. When liquids such as water, brine, milk, etc. flow through tubes without undergoing any phase changes, that means as long as it does not freeze, it should not freeze, but as long as it does not undergo any phase change, the correlations presented earlier for condensers, that means correlations such as Dittus-Boelter or Cedar-Tate can also be used for evaporator. Okay, the exactly same correlations can be used with a small change. In the Dittus-Boelter correlation, for example, you have Prandtl number and the exponent of Prandtl number is 0.4, because there the liquid is being heated as it flows through the condenser, right. But when you use the same expression for evaporator for the external fluid, then instead of using 0.4 for Prandtl number, you have to take 0.3 in Dittus-Boelter correlation, because the liquid is being cooled in case of evaporator. This is the only change, otherwise the correlation will be exactly same. Okay. Now let us look at liquid flowing in a shell. This will happen in shell and tube type of evaporator with dry expansion, where the refrigerant flows through the tube and liquid, that means water or milk, flows through the shell. In direct expansion type shell and tube evaporators, refrigerant flows through the tubes while water or other liquids flows through the shell. Analysis of fluid flow and heat exchanger on shell side is very complex due to the presence of large number of tubes, baffles, etc. Okay, so this is complicated again design point of view, because you can see that there are large number of tubes, again large number of baffles, etc. Okay, so the prediction of heat transfer and pressure drop on the shell side is complicated because of the flow geometry. Okay. Several empirical correlations based on experimental observations have been developed over the years for predicting the pressure drop and heat transfer coefficients on the shell side. For example, you have a simple correlation called as Emerson's correlation, where the Nusselt number is given by Hd by Kf, where Kf is the thermal conductivity of the fluid being cooled, that is equal to C into Re to the power of 0.6, Prandtl number to the power of 0.3 multiplied by mu by mu W of 0.14. Okay, this looks almost similar to your Cedar-Tate correlation for flow through tubes, right. The viscosity effect is there, Reynolds number is there, and Prandtl number is there. Of course, the exponents are different. Here we use Reynolds number to the power of 0.6, whereas in case of flow through tubes we use Reynolds number to the power of 0.8 as long as the flow is turbulent. Okay. And in this expression the constant C depends on the geometry. Okay, that means how the baffles are placed and how many passes are there and all that. Okay, depending upon the specific geometry of the shell and tube type of evaporator, the constant of C has to be obtained and used. Okay, and the Reynolds number Red is defined as RED is ZD by mu, where D is the internal diameter of the shell and G is the mass velocity, which is equal to the mass flow rate divided by the characteristic flow area. Okay, so it has units of kg per meter square per second. So find the Reynolds number from the flow rate and from the area of the or from the configuration of the shell and tube evaporator. Then from the Reynolds number and Prandtl number, find the Nusselt number. Now let us look at boiling heat transfer coefficient, that means heat transfer on the refrigerant side. In evaporators, boiling of refrigerant may take place outside tubes or inside tubes. When boiling takes place outside the tubes, it is called as pool boiling. You might have studied this in your basic heat transfer course, pool boiling. When boiling takes place inside tubes, it is called as flow boiling. The heat transfer coefficients in pool boiling are entirely different from that of flow boiling. Okay. Sometimes flow boiling is treated as a combination of pool boiling and forced convection, and correlations are formulated based on this model. Let us look at some of the pool boiling correlations. In pool boiling, the tube or the heat transfer surface is immersed in a pool of liquid which is at its saturation temperature. This is what is known as saturated pool boiling. The heat transfer coefficient depends upon the temperature difference between the heat transfer surface and the boiling fluid. A pool boiling curve shows various stages of boiling. I am sure that this you must have studied in your basic heat transfer course. If you plot the pool boiling curve, that means the heat flux, okay, watt per meter square, versus the superheat. Okay, that means the temperature difference between the surface, Ts is the surface, Tf is the fluid. And if you gradually increase the degree of superheat, okay, you get a this kind of a curve, right? And you have different regions here. For example, this region 1 is known as natural convection region, and this region is what is known as nucleate pool boiling region, and this is your transient boiling region. Then this you have film boiling. Okay, then here the radiation comes into picture. Okay, so normally all the evaporators or boilers are designed to operate in this region. Okay, this is what is known as your nucleate pool boiling region. Okay. In this region, you can see that the heat flux increases quite steeply with the degree of superheat delta Ts. That means you get very high heat transfer coefficients in these nucleate pool boiling region. Okay, and you can also have normally you have what is known as a critical heat flux, at which the heat flux becomes maximum at a particular superheat. Okay, so if you increase the temperature difference beyond this, then the heat flux has to fall. Okay, and this point is also known as burnout point, which you must have studied in the design of boiling. Okay, so as I said, the refrigerant evaporators are designed to operate in the nucleate pool boiling regions. So the correlations are available for this particular region. So as I said, this I have already explained. So now let us look at flow boiling. Boiling inside tubes is called as flow boiling. Flow boiling consists of nucleate boiling as well as convective heat transfer. That means here the contribution to heat transfer comes from nucleate boiling as well as due to forced convection heat transfer. As the liquid evaporates, more vapor is formed, which increases the average velocity and the convective heat transfer rate. The flow pattern changes continuously as boiling takes place along the tube. For example, in a horizontal tube, the flow can be stratified flow, wavy flow, slug flow, annular flow, mist flow, okay, depending upon the velocity of the vapor. Now let us look at some correlations for nucleate pool boiling. In general, experimental studies show that the nucleate pool boiling heat transfer coefficient HNB is equal to some C into Ts minus Tf to the power of 2 to 3, okay, where Ts is the surface temperature, Tf is the fluid temperature, and C is the constant, the value of which depends upon the surface fluid combination. And the exponent, even though I have shown the exponent here as varying between 2 to 3, it can go up to 25 with treated surfaces. Okay, that means with enhanced surfaces you can get very high heat transfer coefficient. That means the exponent can go as high as 25. Few empirical correlations are available for nucleate boiling. Okay, this is one of the popular correlation, what is known as Roshanov's correlation. So here Cf is the specific heat of liquid and delta Tx is the temperature difference between the surface and the fluid. Hfg is the latent heat of vaporization. Csf is a constant which depends on surface fluid combination, which is 0.013 for halocarbons boiling on copper surface. Okay, and Q by A here is heat flux, mu f is the viscosity of the liquid, Hfg is the latent heat of vaporization. Okay, sigma is the surface tension, Z is the acceleration due to gravity, rho f and rho g are saturated liquid and vapor densities, Prf is a liquid Prandtl number, and the exponent S is 1 for water and 1.7 for halocarbons, and all the properties have to be calculated at saturation temperature at local pressure. Okay, so this is one of the oldest and very popular correlations for nucleate pool boiling. Now let us look at force convection boiling inside tubes. Roshanov and Griffith suggested that flow boiling in tubes be analyzed as a combination of pool boiling and force convection. That means they have obtained total heat flux Q total is equal to QNB plus QFC, where QNB is the heat flux contribution because of nucleate boiling and Q subscript FC is the heat flux contribution because of force convection. Heat flux due to nucleate pool boiling is calculated by using nucleate pool boiling correlations, for example Roshanov's correlation, and heat flux due to force convection can be calculated by using standard force convection correlations such as Dietz-Boelter correlation. Okay, so this is one of the simple way of handling flow boiling. Okay, but this is not very accurate. Okay, it gives reasonably good result but not extremely accurate. We also have what is known as the Beau-Pierre's correlation, which is normally used in refrigerants. This correlation gives average heat transfer coefficients and is valid for inlet quality X inlet varying between 0.1 to 0.16. That means at the exit of the expansion valve and at the inlet to the evaporator, the refrigerant quality should be between 0.1 to 0.16. And the correlation is given here. You can see that here the Nusselt, it is given for incomplete evaporation and it is also given for complete evaporation. The constant is different. Constant is 0.309 for incomplete evaporation and it's 0.0082 for complete evaporation. And here REF is the Reynolds number based on the saturated liquid and Kf is a constant. And Kf is called as a load factor and it is equal to delta X into Hfg by L, where Hfg is the latent heat of vaporization, delta X is the change in the quality and L is the length of the tube. I am sorry, Kf is not a constant, it depends upon the particular situation and also the fluid being evaporated. There is another correlation called Chadok and Brunman's correlation. Again you can see the correlation here. HTP is the flow boiling correlation. HL is the correlation a single phase heat transfer coefficient of saturated refrigerant liquid. Okay, and BO is the boiling number that is given by Q by A divided by HFG into m dot by A, where Q by A is the heat flux, HFG is, as I said, your latent heat of vaporization, and m dot by A is the mass flux. Okay, and here XTT is what is known as Lockhart and Martinelli parameter, and that is defined here. In XTT, the small x stands for the quality, rho g and rho f are the saturated vapor and liquid densities, mu f and mu g are the saturated liquid and vapor viscosities. Okay, so this is one of the correlations used for flow boiling of refrigerants. Okay, let us look at other considerations. Heat transfer correlations will be different for vertical tubes. Presence of lubricating oil affects the heat transfer coefficient and pressure drop if the oil concentration is high. Heat transfer enhancement on refrigerant side is possible by employing force feed recirculation, integral fins, turbulence promoters, treated surfaces, etc. However, enhancement techniques also increase pressure drop. That means we have to optimize the enhancement techniques so that you get high heat transfer coefficient, at the same time the pressure drop is not very high. Okay, so these are the considerations. Now let us quickly look at what is known as the Wilson's plot. This is a technique to determine the individual heat transfer coefficients from the experimental data on heat exchangers, for example condensers and evaporators. Okay, so from the experimental data on these heat exchangers we can find individual heat transfer coefficients. For example, take a water cooled condenser. A number of tests can be conducted by varying the flow rate of water and measuring the inlet and outlet water temperatures. From energy balance, we have this equation QC is equal to MW CPW into delta T for the water side, which can be measured, and this is equal to U naught A naught into LMTD. Since LMTD can be obtained because we are measuring the temperatures, A naught is known. So from this expression you can find out the overall heat transfer coefficient from the experimental measurements. With negligible scale formation, the expression for U naught is given here. Okay, this we have discussed in the last class. This is the expression for U naught. And if the water temperature does not vary significantly, then property variation will be negligible, and if the flow is turbulent, then the internal heat transfer coefficient, that is on the water side, is proportional to V to the power of 0.8. That means Hi can be written as some C into V to the power of 0.8. Okay, as long as the property variation is not considerable. And heat transfer coefficient on refrigerant side and wall resistance remain almost constant because we are not varying the refrigerant side flow rate or the operating conditions. Then a plot of 1 by U naught versus 1 by V to the power of 0.8 will be a straight line. Okay. So if you plot 1 by U naught, okay, versus 1 by V to the power of 0.8, then you get a straight line like this, and the intercept gives you the resistance on the refrigerant side plus wall resistance, because that remains constant, whereas the resistance on the water side will be varying because the velocity of the water is varying. Okay. From the intercept we can calculate the condensing heat transfer coefficient, as the resistance of wall can be easily found. The exponent will be different for air cooled condensers. That means for air cooled condenser it can be done with air or water or any other fluid. You have to use 0.65 in place of 0.8. Fouling resistance can be included if its values is known. Okay, so this is a very useful concept, and it is normally used for obtaining the condensing heat transfer coefficients, etc. Okay, so at this point I stop this lecture. Okay, so we have completed our discussion on evaporators. So I will continue this in the next lecture. Thank you.